Hi everyone. Uh, Welcome to chapter 5 of Chemistry 105. In this chapter, we're going to talk about water and solutions. Okay, here are some questions in this chapter we need to answer. In the first part, of course, we want to talk about water and what makes water special and what are the unique properties of water and where is the water located and we and other life forms use, and how does water interact with the other chemicals. And in the second half, we wanted to talk about how do the properties of water change through its interaction with other compounds, and also how can we improve the quality of water. So let's take a look. Some data, some charts, and some numbers to give you an overall picture of the water for life. Okay, first, the water we drink. Okay, water we drink. Our planet is covered by water, of course, by seawater. Okay, it covers 70% of the Earth's surface. And also water composes of 60% of the human body. Okay, most over 60%. 50% of our blood and 77% of our brain. Okay, and water is essential for life. Apparently, human can only go a few days without water. Okay, without water. Now, however, even though water is important, water is, or even though our planet is covered by water, but water is a very limited source. Okay, this pie chart shows you the reason. Okay, it shows you the reason. Earth's water, even though 70% of the surface of water of the Earth is covered by water, what's going on? Why it's not? Sorry, we're back. Now, even our planet Earth is covered 70% by water, but 97% of the water is seawater. Okay, is seawater. And well, let me see how to change the slides to a. Sorry, give me 1 second. Okay, 97% of water is seawater, and 3% of water are fresh water that we can use. However, among those 3%, majority of the water, or 68.7%, are stored in ice caps and glaciers. So we're looking at, and also 30.1% are underground groundwater. Sometimes it's hard for us to dig out for use. So we're looking at 0.9% of other water, which are surface water, and others including 0.3% of surface water that are located or contained in lakes and swamps that are really usable fresh surface water. Okay, surface water. So sometimes people can give you like an approximation that if all the water on our planet fit into a 2-liter bottle, and only 60% will be fresh water, and among those, only 4 drops will represent the water in lakes and rivers. Okay, if you assume 20 drops per liter, you can do a simple math to see if the statement is correct. Okay, is correct. Out of a 2-liter bottle, only 4 drops will represent water that are lakes and rivers. Okay, and this chart shows you the water use trend. Okay, in the United States, 322 billion gallons of water are withdrawn daily in the U.S. 86% fresh water and 14% seawater. And thermal electric power and irrigation represent the largest use of waters. Okay, of course, agriculture accounts for 30% of water, global water average. So you can see that in this chart, the public supplies, irrigation, thermal power, how much used water are consumed by year. And this picture shows you the excess of safe drinking water across the world. You can see that greener color, okay, greener color in North America, in North America and in East Asia, those countries have generally safe or larger percent of access to safe drinking water. But you can see that in African countries, a lot of countries have very well below 60% or even below than 50% of access to safe drinking waters. And usually our water is the water we use daily are free of pollutants, okay, but groundwater can also be contaminated by a few factors such as abandoned mines and something from fertilized fields, poorly constructed landfills, and also some household chemicals poured down the drain to the ground, get to the ground. Now, all these are data for showing you water is a limited source, but someone asked, is there a way we can convert? Okay, we can convert seawater, or how do we convert seawater, which is stored in greatest amount on our planet Earth, into fresh drinking water? Okay, one of the techniques we can do that is called distillation. Okay, distillation. This is on the left picture shows you a device, a lab scale device of distillation, which is you heat seawater, okay, or even contaminated water, and then the water vapor is going to be condensed by a condenser, which is running coolant or cold water. Then you collect the water, and we call those water distilled water. Okay, of course, this process requires a lot of energy. For example, you need heat, but sometimes we can use solar power, which is free energy, to conduct distillation. But the scale is relatively small if you're using distillation. Okay, another technique we can use to convert fresh water from seawater is called reverse osmosis. In order to explain what is reverse osmosis, you first need to know what is osmosis. Okay, osmosis. Osmosis is basically the passage of water through a semi-permeable membrane. A semi-permeable membrane is a membrane that's designed so that large molecules like particles in solutions will not pass through. Only small molecules like water can pass through freely through that membrane. So if two solutions like fresh water and seawater are separated by the membrane, okay, the direction of water flow, or we should say the net direction of water flow, will be from the freshwater side into the seawater side. So you're actually losing fresh water. That's the natural, spontaneous direction of water flow. We call that osmosis. Okay, the solution, the direction is always from less concentrated or fresh water to a more concentrated, such as seawater. Now, if you want to reverse that process, reverse the osmosis process, you need to add extra energy. Here, in this case, we need to add some pressure to reverse that osmosis process. So that's why this technique is called a reverse osmosis, to use pressure to force the movement of water through a membrane from more concentrated to less concentrated. So you're basically getting water from seawater into pure water, okay, to purify water. And that device can be used as a boat. You can see this young man is using a reverse osmosis process on a boat. So you can convert seawater into safe drinking water. Get a safe drinking water. And chapter 5 discussion is a topic related on this as well. So related, how do we convert seawater into fresh, safe drinking water, called seawater desalination, okay, desalination. And this is, I think, 2 videos asking you what are the current stage, what do we know about, or what are techniques used about seawater desalination, and also why this technique is not used in large scales. What are the limitations that prevent us getting fresh water from seawaters? Okay, seawaters. And this is another device that can be used under emergency called a live straw, which is basically a filtration device. You can under emergency, like you're outside, you're outdoors, you're in the woods, or hiking or camping, you need fresh water, safe drinking water. You can drink from a pond, for example, but that's still in a personal, the small scale. And this is an article. I think the link is in your notes as well. In July 2018, liquid water lake was revealed on Mars, so showing there's a possibility of water in other planet in our solar system. So these are some brief introduction about water issues, some data, but next, importantly, we want to study some chemistry of water. Why water is so special, why water has, or what property does water have to make it the most important solvent in our planet. Okay, first, let's take a look. What are those important but peculiar properties of water? Peculiar means some properties are not expected by our expectations. So if we want to talk about molecules, we want to deduct the property from molecule to another. Water has very peculiar properties. So the first peculiar property is water is a liquid at temperature. Okay, comparing with other molecules with similar molecular weight, okay, such as nitrogen, oxygen, and carbon dioxide. These molecules are similar molecular weight, but these are all gases. Even carbon dioxide has higher molecular weight, much higher than water, but water is a liquid. Okay, number two is related to that. The reason water is a liquid at room temperature and is because water boiling point is very high, is relatively high. Okay, water has a anonymously high boiling point of 100 degrees Celsius. Okay, 100 degrees Celsius, and much higher than even, not to say these gases, much higher than other liquids. Okay, other liquids. And another peculiar property is when water freezes. Okay, water freezes meaning water change from liquid to solid. The volume is expanded. Okay, expanded increases. So basically means when you have the same amount of water, okay, the mass will be the same, but when you change the water from liquid to gas, the density of water is going to decrease because the volume is increased when water solidifies. And that is the only solid so far we found, substance that has this property. Most substances or most matters, when they solidify, their density is going to be bigger because solid are more tightly packed in together than when it's liquid. We have seen that picture in chapter 1. When particles are liquid, particles in a liquid is not as tightly packed as particles in a solid, but water is an exception. Okay, in order to explain these peculiar properties of water, first we need to take a look at the structure of water, and especially the bonding of water, the atoms in a water molecules. Okay, here a review of different representation of water, including showing how electrons are shared between hydrogen and oxygen, and also the Lewis structure showing the bonding between oxygen and hydrogen. And in chapter 3, we also studied there are 4 electron groups around the central atom of oxygen. So these 4 electron groups, including 2 single bonds and 2 lone pairs, adopt the geometry called the tetrahedral. However, there are 2 lone pairs with 2 bonding electrons. So the derived geometry of the water molecule is called bent. That's why we have a model of water molecule is a bent shape. 2 hydrogens are on the sides of the oxygen. So that's how water hydrogens are bonded with oxygen and what is the geometry of water. Now, after we know that, let's take a look. Close look at the OH bond. Okay, OH bond. When oxygen and hydrogen are bonded together, they're sharing electrons. Okay, they're sharing a pair of electrons basically between the oxygen and each one of the hydrogen. Now, when atoms share electrons, in a covalent bond, the sharing is not always equal because different atoms have different attractions to the shared electrons. Some atoms attracts electrons stronger, some atoms attract electron weaker. So there is a measure of an electron's attraction for the electrons shared in a covalent bond. And that measure is called electron activity. Okay, electron activity. Electron activity basically means how strong that atom attracts electrons in a shared covalent bond. Okay, covalent bond. Now, if an atom attracts electrons stronger, that atom has stronger electron activity. If an atom attracts electron not as strong, then that atom has weak electron activity. Non-metal atoms normally they attract electrons, but non-metal atoms normally attracts electrons stronger than metal atoms. And in our periodic table, there is a trend regarding this attraction, regarding this electron activity that is shown in this chart. You can see that the electron activity actually can be quantified. You can see that each element under there's a number showing you the electron activity value. Stronger, again, bigger value means stronger attraction, means stronger electron activity. Again, the trend in the periodic table is if you move from left to the right across a period, the electron activity is increasing. Okay, and if you move from bottom to top across a group, across a column, the electron activity also increases. Or you can see from top to bottom, the electron activity decreases. So that means the elements with the strongest electron activity will be always around the top right corner of the periodic table. Again, you don't consider noble gas because noble gas, they have octet, they have 80 electrons. They don't have attract electrons in a covalent bond. So elements with strong electron activities will be always, they're accumulated in what? In the top right corner of the periodic table. And among these elements, oxygen, fluorine, chlorine, nitrogen, etc., fluorine is the most electron active element because think about the trend from left to right, increase, from top to bottom, decrease. So the top right corner one is the one with the strongest electron activity, that is fluorine. You can see the fluorine value 4.0 is higher than all other elements. But also you can see that from here, non-metals, nitrogen, oxygen, sulfur, chlorine, have higher electron activity than metals because they attract electrons. They like electrons. And because of that, when atoms share electrons, but they have different attraction, okay, different attraction for that shared electron, that difference causes the unequal share of electrons in a covalent bond. And that unequal sharing of electrons in a covalent bond is called a polar covalent bond. Okay, covalent bond, such as the bond between oxygen and hydrogen. If you look at the electron activity, oxygen has an electron activity of 3.5, hydrogen has only 2.1. So apparently there's a difference of 1.4 electron activity between O and H. Oxygen has stronger electron activity. Oxygen will attract more electron towards itself. Hydrogen will not be as attracted as much. So because of that, that bond between O and H is called a polar covalent bond because the electrons are not equally shared. Oxygen attracts electron more towards itself. And because the electrons are negatively charged, oxygen attracts electrons more towards itself, making oxygen, the atom oxygen, bears a slight or partial negative charge. That delta negative means a partial charge because they're still sharing, but oxygen shares slightly more electrons, making oxygen bear a partial negative charge. And of course, hydrogen will bear a partial positive charge, a positive charge. And that unequal share and also that charge distribution, we call that a dipole, okay, a dipole. In order to represent a dipole, we have two ways. One way, again, is to mark the charge. The atom with stronger electron activity, such as oxygen in this picture, is marked as delta negative. The hydrogen is marked as delta positive. Another way of representing a dipole is you draw an arrow. The head of the arrow is pointing towards the more electronegative element, and also the tail of the arrow, you use a cross. Okay, you use a cross. And you can also see the picture between the O and H, when even though share electrons, the electrons are cloud, share the electron cloud, but oxygen takes most of the electron cloud towards itself. So there is a dipole between the O and H pointing the oxygen, okay, pointing oxygen. And that again is called a polar covalent bond, okay, a polar covalent bond. Now, with that understanding, now you have we can show you a bigger picture of what is a chemical bond. Okay, what is a chemical bond? Different types of chemical bonds is actually only relying on the difference between the shared electrons, the electron activities of these two shared atoms. Okay, for example, in this chart, you can see that if A and B are making a covalent bond by sharing electrons, but if A and B have similar electron activity, so that means the difference between the A and B electron activity are very small because their electron activity different. If the difference is between 0 and 0.4 difference electron activity wise, then the A and B, these two atoms will share electrons equally or close to equally. If that's the case, you can see that the electron clouds are equally distributed on A and B. If that's the case, we call that bond a nonpolar covalent bond. Okay, nonpolar covalent bond. Again, how we have a nonpolar covalent bond is when A and B share electrons equally or close to equally. And the difference, delta En here, delta En, which is the electron activity A minus electron activity B. I don't know why that's show here. Delta En equals to electron activity of A minus electron activity of B. Okay, so the difference is small between 0 and 0.4. If that's the case, the bond is called a nonpolar covalent bond. Now, if the electron activity of A and B difference start to get bigger, so means one of the atom has greater electron activity than the other, so they have a bigger difference. If the difference is between 0.4 to 2, that means their difference is big. If that's the case, the bond between A and B still sharing electrons, but that bond is called a polar covalent bond. Polar covalent bond, of course, meaning A, for example, in this case, shares more electrons, has greater electron activity. So A bears a partial negative charge and B bears a partial positive charge. Okay, and that there's a dipole involved in the polar covalent bond. And but again, these two atoms are still sharing electrons, but the share is no longer equal. That's the case. We call that a polar covalent bond. Now, if you think about another scenario, which we can talk about more in this chapter later, in the second part of this chapter, is when A and B electron activity are too big different, such as one is a metal, one is a non-metal. So, for example, if you look at this chart, the metal and non-metal, the electron activity difference is very big, such as lithium and fluorine. For example, lithium is 1, fluorine is 4. The difference is 4 minus 1 is 3. If that's the case, okay, that's the case, these two atoms will no longer share electrons. One of the atoms will completely take the electrons away from another atom. They won't share anymore. So if that's the case, there will be no sharing. Then electrons will be completely transferred from one to another, resulting in a new type of bond called ionic bond. Okay, ionic bond. So you can see that in chemistry, different types of bonding is not really has a clear limit. They're actually continuous. But normally we consider when the electron activities are smaller, difference is smaller, they form covalent. And even they're covalent, there are two types of covalent, polar versus non-polar. But if their electron activity is too big, like greater than 2 and greater than 2, then their sharing won't happen. One of the atoms with greater electron activity will completely take the electrons away, transfer of electrons. And that's the case, we get ionic bond. So this is the bond type versus electron activity difference. It matters how big different they are. Okay, how big different they are. Now, okay, this is a chart asking a simple quick question, asking you compare the bond given in each option, asking you which one is more polar, which one is less polar. Okay, remember we said earlier, a polar bond means two atoms share electron unequally. Okay, unequally. That means if the difference, the reason they have a polar bond is because two atoms have different electron activity. So greater difference, meaning what? Their sharing is more unequal. If that's the case, the bond will be more polar. So the question, which one is more polar, basically asks you which pair has greater difference with electron activity. For example, okay, A asks you to compare HF1 and HCl bond. Okay, remember that in this case, you don't even need the value because we know that if fluorine and chlorine are both bonding with hydrogen, then we only need to ask ourselves, fluorine and chlorine, which has greater electron activity? We know fluorine has on top on the periodic table, chlorine is lower than fluorine. So fluorine has higher electron activity, making the difference between F and H greater than Cl and H. If that's the case, FH bond has greater difference than HF bond has bigger polarity, which is more polar, okay, more polar. And very similarly, NH bond and OH bond, okay, for example, NH bond and OH bond, between NH and OH, all you need is compare between N and O. Oxygen is on the right of the nitrogen, so oxygen is more electron negative, and because of that, OH bond difference will be bigger than NH bond, so OH bond is more polar, okay, more polar. Again, polar bond means electron activity is different. More polar means greater difference between the shared elements. Okay, C, I believe you need to plug in numbers to calculate which one has greater difference between N and O and O and S. Okay, you can do the simple math. I gave you the chart down there to do that simple difference to see which bond is more polar. NO bond is more polar, or OS bond is more polar. Okay, more polar. Now, this is, we're talking about a bond. Okay, bond between two atoms. Okay, bond between two atoms. But a chemical bond does not determine a whole molecule. So after we understand the polarity of a bond, let's take a look. How about a molecule? Okay, how about a molecule? Okay, because again, a bond sometimes doesn't represent a whole molecule. So how about a molecule? How do we determine whether a molecule is polar or not? Or how do we know the difference between bond polarity and molecular polarity? Okay, these are two scenarios. The first scenario is if a molecule only has one bond. Okay, one bond. If that's the case, okay, then the bond polarity will determine the molecular polarity. Okay, for example, these two molecules, hydrogen and oxygen. Okay, hydrogen and oxygen, they are only one bond. Hydrogen bond or oxygen bond. If that's the case, if the bond is polar, the molecule is polar. If the bond is nonpolar, the molecule is nonpolar. For example, hydrogen bond and oxygen bond are both nonpolar bond because they're the same atom. Their electron activity is the same. So if that's the case, both bonds are nonpolar, then both molecules are also nonpolar. Okay, because molecules contain only nonpolar bonds, must be nonpolar. Okay, if that's one scenario. Now, a more complex the molecule, okay, more complex the molecule, such as molecule containing 3 atoms or multiple covalent bonds. If that's the case, that molecule may either be polar or nonpolar, regardless, even the molecule contains a polar bond. Okay, molecule containing polar bond may either be polar or nonpolar bond if the molecule has multiple atoms. And that, whether the molecule is polar or nonpolar, depends not only on the bond, on each individual bond, but also depends on the geometry of the molecule, okay, on the geometry of the molecule. For example, here, water. We know in water, the OH bond is polar. It is the dipole. pointing what? Pointing to the oxygen, because oxygen is more electronegative. And because the geometry of water is bent, these two dipole arrows cannot cancel each other, because bent, if you think of bent as two direction forces, they're both pointing, one is pointing up right, one is pointing up left. So they're actually both pointing up. These two dipoles don't offset or cancel each other. If that's the case, these two polar bonds don't cancel each other, resulting a polar water molecule. So you can see that water molecule, it has polar bond, but the geometry is bent, so the molecule itself is also polar. On the other hand, beryllium, beryllium chloride, beryllium chloride, it has two bonds as well. Two bonds as well. Each bond, Be and Cl bond, is polar. Chlorine is more electronegative, so it has a dipole point to chlorine, has another dipole point to chlorine. Dipole point to chlorine. However, the geometry of beryllium chloride is linear because of two groups. The geometry is linear. So it's a symmetrical molecule. And because of that, these two dipole, one to the left, one to the right, offset, cancel each other. So the molecule itself has no dipole at all because these two dipole cancel each other. And because of that, beryllium chloride is a non-polar molecule. You can see that both molecule contains polar bonds, but water is polar. Beryllium chloride is non-polar. The reason lies in what? The geometry. Water is a bent geometry. The dipole moment don't cancel each other. Beryllium is a linear geometry. These two dipole cancel each other. These two dipoles cancel each other. And here is a very simple comparison between water and carbon dioxide, asking you why carbon dioxide is nonpolar, even though CO bond is polar. But why carbon dioxide is nonpolar? The same reason I want you to be able to understand. I give my work and answer here, but you can hope you understand the reasoning. When a molecule contains polar bond, it does not necessarily mean the whole molecule is polar or nonpolar. You have to consider what? Consider the geometry. Water molecule, in particular, because the bent geometry is not considered a symmetrical geometry. The symmetrical geometry, the dipole can cancel each other. If a dipole, these two dipole moments cannot cancel each other, we don't consider the geometry as symmetrical. A water bent geometry is a asymmetrical geometry. So again, water, asymmetrical, bent. Asymmetrical bent. There are two dipole moments, one point here, one point here. These two can kind of cancel each other. So this will result a polar water molecule. Now, when water molecule is polar, it actually means the charge distribution in this whole water molecule is not evenly distributed. The oxygen side of water on this here end has more negative charge, because think about the both two dipoles pointing to the oxygen. So the oxygen of the water, the oxygen of the water has more negative charge, partial negative. The hydrogen side of the water has more positive charge. So that's why in the whole water molecule, you can see the charge is not evenly distributed. One end has more negative, one end has more positive. And because of that, water molecule, again, is called a polar. And because the charge is not evenly distributed, when you have a bunch of water together, the water molecule is going to interact with each other because charge interaction. The hydrogen of one water can interact with the oxygen of another. The oxygen of another water can interact with the hydrogen of another. You can see the dashed lines are showing you the hydrogen-oxygen interaction between water molecules, between different water molecules. We call that dashed interaction because of charge. Again, oxygen has partial negative charge, hydrogen has partial positive charge. So because the negative partial positive charge between water molecules, we call those interactions a hydrogen bonding. Hydrogen bonding. The hydrogen bonding is a electrostatic attraction between hydrogen and oxygen, in this case, water. Okay, in this case, water. And hydrogen bonding are intermolecular bond. Okay, intermolecular means across different molecules, not within a molecule. Okay, in comparison, covalent bond, the solid lines are intramolecular, means they're within a molecule. But hydrogen bonding are talking about the interaction between different molecules. Because of what? Because water has uneven charge distribution. The oxygen can interact with the hydrogen of another water, and we call that hydrogen bonding. Now, hydrogen bonding is not like a universal, we should say. It has to satisfy two conditions. One is hydrogen bonding, you need to have hydrogen. Okay, hydrogen, which is a small atom, and hydrogen must be bonded to a highly electronegative atom, such as oxygen, nitrogen, or fluorine. Okay, in water, of course, it's oxygen. Okay, you have to satisfy both conditions. Then you can expect hydrogen bonding. Again, hydrogen and hydrogen must be bonded to a highly electronegative atom. Okay, remember, oxygen, hydrogen, fluorine are highly electronegative atoms. They're small, they're highly electronegative. If that's the case, we have a special term called hydrogen bonding. Okay, hydrogen bonding normally is not as strong as covalent bond because they're across different molecules. They're intermolecular bonds, but they're relatively strong comparing with other type of molecular interactions. Okay, normally hydrogen bonds are about 1/15 as strong as a covalent bond, which is fairly strong already, considering it is a intermolecular bond. Of course, in water, hydrogen bonds play a major role to explain the peculiar properties of water. Okay, now you know what is hydrogen bond. The dashed lines between the hydrogen and the oxygen of a different molecule. Of course, if we have a lot of water molecules, you have a huge network of hydrogen bond. And those hydrogen bonding explained why water have many peculiar properties. Okay, the first peculiar property, like we said, is water is a liquid, and water has a high boiling point. Okay, the reason lies in hydrogen bonding. Okay, hydrogen bond. You can see that again, each water molecule has charge distribution. Oxygen has partial negative, hydrogen has partial positive. And because of that, if you have a bottle of water, the water molecule is going to interact with them with a lot of hydrogen bondings, the dashed lines. And because of that, separating water molecules, boil water molecule. Remember, boiling is what? Changing from liquid to gas. Water molecule need to be separated. Separating water molecule going to take a lot of energy because, like we said, hydrogen bonding is not as strong as covalent bond, but is a relatively strong intermolecular bonding. And because of that, strong interactions, separating water molecule is harder than separating molecules of similar types. You can see that here they're comparing H2O, H2S, H2SE, oxygen, sulfur, selenium. They're in the same group, so we're comparing the similar type of molecule, H2O, H2S, H2SE. Normally, the boiling water predicted will be here if we talk about these molecules similar. But the actual boiling point is what? You can see the much higher than the rest of this H2S, H2SE, H2T. The reason is what? The reason is relatively or peculiarly strong hydrogen bonding. And because of these network of hydrogen bonding, making boiling water needs extra amount of energy. And that results in what? Extra high boiling point. Because you need to break the hydrogen bonding to transform water from liquid to gas. Okay, that's how we use hydrogen bonding to explain the peculiar property of water. Again, you see that if we want to explain hydrogen bonding, we need to explain why water has charges, has partial charges, or uneven charges distribution across the whole molecule. Okay, another property, if you remember, water expands. Okay, water expands when freezes. Can also be explained by hydrogen bonding. Okay, remember, water molecules are interacting with each other by hydrogen bondings. Okay, hydrogen bondings. But when water freezes, the water molecules is going to be more organized, even though before and after liquid water and solid water, the water molecule is always hydrogen bonded. But when water is free, the hydrogen bonding is not as stable as when water is a solid. Or we should say when water is a solid, the water molecules arrangement is more organized. And because of that, there are cavities or pores. The structure of ice has more holes or pores than liquid water. So making the volume water expands. Here is more explanation here. Okay, when water freezes, because of the organized hydrogen bonding, empty space will be created in the form of hexagonal channels in ice. Okay, you can see that this is the crystal structure of ice. You can see water molecules are very beautifully aligned and organized, and water molecules will form a hexagon channel, and that channel is some extra space. Okay, extra space, making solid water less packed or less tightly packed than liquid water. Okay, even though liquid water, the water molecules are interacting with each other, but because of the organized arrangement of water, because of the organized hydrogen bonding, the water molecules will be creating a hexagonal channel, which is some extra space in ice water, okay, in ice form of water. And because of that, the volume of water is going to be bigger when solid, okay, when solid. And when volume is bigger, okay, there's a term called the density, which equals to mass over volume. Okay, when water freezes, the mass doesn't change, but when volume is bigger, the density of ice is going to be smaller because volume expands, mass sustained. So the density of ice is smaller than the density of water. That is a very important property because most substances, the density of a solid will be greater than liquid. Only water, the density is smaller. That will make ice, float on the surface of lake and river during winter times, when temperatures low and water freezes. Water freezes from the surface to have, so that will actually give us a insulating layer to give those living creatures in water a livable or good environment for them to survive the winter. Okay, if you think about it, if water freezes from the bottom of lake, then it will be a different scenario on our planet Earth. And because of that, okay, because when water freezes, the density is smaller, it floats on the surface of lake and river. This property actually makes life possible on the planet Earth. Okay, on the planet Earth. So this property behavior means that the surface ice often covered by snow can act as an insulator that keep the lake and water beneath from freezing solid. Okay, from freezing solid. Okay, here's a quickly practice. I show you my answer here. Asking you not only demonstrate what is hydrogen bonding. Okay, use dashed lines between water molecules, between the O of one molecule and the hydrogen of another water mix, but also ask you to show people when you boil water, which bonding or which interaction is broken. Okay, we're actually breaking hydrogen bonding when you change water from liquid to gas state. Okay, gas state. Now, before we move on to part 2, we have one extra peculiar property which is not explained by hydrogen bond, but also important peculiar property of water is the specific heat of water. Okay, what is specific heat? Specific heat basically means how much energy do you need to increase 1 gram of substance by 1 degree Celsius. So you heat the substance, you heat 1 gram of substance. If you want to increase the temperature of that substance by 1 degree Celsius, how much heat do you need? Water, this substance, has the highest specific heat of any substances. The value is 4.184 joule per gram per degree Celsius. So basically means if you want to raise the temperature of water, of 1 gram water by 1 degree, you need 4.184 joules of energy, which is higher heat than all other substances. You can see this is the specific heat of water, which is higher than metals, non-metals, and mineral substances. This tells us what? This tells us when you heat water, okay, when you heat it, because it takes a lot of energy for water to heat up. So the temperature of water does not change much when the weather changes. Okay, when weather changes, because it takes a lot of heat to warm up water. Okay, unlike metals, for example, here's an example showing you. If you heat with 1 calorie of 1 calorie of heat, okay, some substance, the temperature will rise 20 degrees, like gold will rise 30 degrees, but water temperature only rise what, 1 degree or 2 degrees. Okay, the reason is it takes a lot of heat to rise the temperature of water, and this tells us temperature of water doesn't change when weather changes. Okay, when weather changes, and that also guaranteed our planet Earth is the temperature of our living environment doesn't not like the temperature span or temperature gap of our living environment doesn't change a lot. Okay, think about if your water temperature change a lot as the temperature or an atmosphere temperature changes, then our water won't be a living environment for a lot of living things. Okay, this is not a picture show you for 100 grams of calories of heat. Okay, the rock temperature is going to change from 25 to 30 degrees, 5 degrees. But the same amount of heat, you can only change the same amount of water by 1 degree. Okay, so that tells us again, if you live around water, okay, your temperature, your atmosphere temperature won't change much as when you live in mountain or desert area. If you're in the desert, we know that during the daytime, because of sunlight, the temperature is going to be extremely hot, but during the night, the temperature is going to drop extremely low. Because what? Because the specific heat of sand is small compared to water, okay, compared to ocean when you're living near the coast. So that's another peculiar property of water called specific heat. So that is the first part of chapter 5. We talk about some water issues. We talk about some facts about water, and we also discuss briefly what are the techniques, even they're simple, but small scale techniques. How do we convert seawater to fresh water? And also we explained the bonding of covalent bonding and the types of bonding related to electron activity. And also we talk about how do we determine a molecule, whether it's a polar or not. And by using that, we use hydrogen bonding to explain the peculiar properties of water. Okay, we're going to stop here and we're going to continue in part 2 of chapter 5 to talk about when water acts as a solvent for particles that can be dissolved in water. We call solutions. Okay, and we'll continue on chapter 5, part 2.